Hello everyone, very good evening to all of you. Good evening everyone, good evening, good evening. Am I audible and visible? Good evening Mithun, good evening, good evening. So am I audible and visible? So please type in a chat box. Everything is okay, audio and video both are fine. Thank you so much beta, thank you. Means a lot, thank you so much. Okay, so shall we start today's session? So beta, whatever we discussed in the previous class, that is clear to everyone. Whatever we discussed in a previous class, that is clear to everyone. Shall we start today's session? Shall we start today's session? Okay, so before moving to the next topic or before moving to the next fluid property, let's try to solve some problems, right? Let's try to solve some problems on the basis of previous concept, right? Let's try to solve some problems, right? So this is the one problem. This is the NAT problem, right? This is the NAT problem. So please read the question carefully first. Please read the question carefully first. This is a NAT kind of problem. So in question, there is a shaft with a diameter of 80 millimeter, right? Shaft with a diameter of 80 millimeter and length of 200 millimeter. Shown in the figure is pulled with a constant velocity of 4 meter per second through a bearing with variable diameter. Fine. The clearance between the shaft and the bearing, which varies from H1 1.6 millimeter to H2 0.4 millimeter, is filled with a Newtonian lubricant whose dynamic viscosity is 0.10 pascals second. The axial force required to maintain the axial movement of the shaft in Newton is, right? And round off to 2 decimal places. So beta, this is the shaft, right? This is the shaft, and diameter of the shaft is mentioned 80 millimeter, right? Diameter is mentioned 80 millimeter, and the length of the shaft is 200 millimeter. Length of the shaft is 200 millimeter, right? And this shaft is moving. This shaft is moving with a velocity of 4 meter per second. This shaft is moving with a velocity of 4 meter per second. So to move the shaft with velocity of 4 meter per second, we apply some forces. So in question, that force is asked, right? So let us consider that force is F. That force is F. Now, to reduce the friction, lubricant is used. Lubricant is used, and that lubricant follows the Newton's law of viscosity, right? And at this particular section, right, at this particular section, that gap is H1, and at this particular section gap is H2, and H1 is given 1.6. H1 is given 1.6 millimeter, and H2 is given 0.4 millimeter. 0.4 millimeter, right? And dynamic viscosity of the lubricant is mentioned 0.10 pascal second. 0.10 pascal second. So in question, F is asked. Okay, so concept related to this problem we already discussed in the previous problem, right? Concept related to this problem we already discussed in a previous class, in a previous session, right? And beta, I already told you, whenever you are getting such kind of problem where that gap is linearly varies with respect to the length, right? Let us consider this is x is equal to 0 and let us consider this is x is equal to L and this is the x direction. Right? So whenever you are getting a problem where gap is linearly varies with x, right? So can we write directly, can we write mathematical expression directly? Can we write mathematical expression directly? We already solved this problem na? In the previous class. We already understand the concept behind this problem. Is it okay? Okay, so do one thing. Beta, if there is a, let us consider if there is a shaft, right? Let us consider another case. Let us consider this case. So this shaft is in the sleeve or bearing, you can say, right? This shaft is in the sleeve or bearing. Fine. And in this particular case, H is not function of x. In this particular case, beta, H is not function of x. So this is the lubricant, right? This is the lubricant. So in this particular case, This is the H. This H is not function of x. This H is not function of x. Let us consider this is the x direction, right? And what is the diameter? Let us consider the diameter is di. And I am applying a force F, right? I am applying a force F to pull this shaft with a velocity of, with constant velocity of u. So in this case, what is the F? Can you find out the F? So this is very simple, na? That F is equal to, this is the tau multiplied by shear area. And tau you can write beta, this is from the Newton's law of viscosity, this is mu du by dy into what is the area? So that area is nothing but this is the pi di into L, right? Pi di into L, right? And this is also equal to, if velocity profile is not mentioned, then we can consider linear velocity profile. We can consider linear velocity profile in the lubricant. So directly we can write this is u minus 0 divided by H multiplied by pi di into L, right? So this is the mu u pi di L divided by H, right? This is the force which is required to pull the shaft with a constant velocity of u, right? So for this particular case, this is the F. And beta, whenever H linearly varies with x, H linearly varies with x, H linearly varies with x, then we can directly write that F is equal to, F is equal to mu v mu u pi di L divided by HM. And what is the HM? In this case, what is the HM, beta? What is the HM? Tell me, what is the HM? Tell me, what is the HM? That HM is nothing but the logarithmic mean of, logarithmic mean of H1 and H2. So simply you can write this is equal to H1 minus H2 divided by natural log H1 by H2, right? H1 minus H2 natural log H1 by H2. So this is the HM, right? Now calculate HM directly. So that HM is equal to, this is the H1 minus H2 divided by natural log H1 by H2, or you can say H2 minus H1 upon natural log H2 by H1. So what is the H1? Tell me, what is the H1? That H1 is 1.6 millimeter. 1.6 minus 0.4 natural log 1.6 divided by 0.4. So tell me, what is the HM? This HM is in millimeter, right? This HM is in millimeter. So tell me, what is the HM? Yes, very good. So tell me, what is the HM? What is the HM? So this is 1.6 minus 0.4 natural log 1.6 divided by 0.4. Right, so finally what you are getting? You are getting, this is 0.8656 mm. Everyone getting the same thing? Everyone getting the same data? That HM is 0.86556 millimeter. Okay. And once you know the HM, then you can easily calculate the F. So that force required, the force required to pull the shaft with constant velocity u, so that is mu multiplied by u. And what is the mu? Mu is 0.10. This is 0.10 Pascal second multiplied by u. U is mentioned 4 meter per second multiplied by pi DIL, pi into, what is the DI? What is the DI? The DI is 80 millimeter, na? Right? DI is the 80 millimeter. So 80 into 10 to the power minus 3 meter into, so pi into DI into L. L is 200 millimeter. So this is 200 into 10 to the power minus 3 divided by HM. And what is the HM? That HM is 0.8656 into 10 to the power minus 3. Right, so this comes in Newton. This comes in Newton. So tell me, what is the answer that you are getting? Right, so 10 to the power minus 3, 10 to the power minus 3, 10 to the power minus 3 is cancel out. Right, so this is 0.10 into 4 into pi into 0.10 into 4 into pi into 80 into, okay, just 1 minute, na? 0, 0, 0, 10 to the power minus 3. Okay, fine. So pi into 8 into 2 and 0.8656. So this comes 23.228 Newton. Everyone getting the same answer? Please let me know. Everyone getting the same answer? 23.228 Newton. Everyone getting the same answer? 23.228 Newton. Right, 23 point. So that answer is if your answer is in this range, right, 23 to 23.4. So that is correct. Okay, so this is the correct answer. This is the correct answer. Sahif, please check your calculation part now. It is not 0.023, it is 23.3. 23.3 or 23.228 Newton. This is the right answer. So please check your calculation part. Okay. Now it is clear? This question is clear or not? This question is clear or not? This question is clear or not? Okay. Now come to the next question. Very beautifully framed question. Come to the next question. Very beautifully framed question. Right? Please see this question. Okay. This is the NAT problem, na? This is the NAT problem. Font size is okay. Font size is okay. This question is readable, na? Okay, font size is okay, fine. So two immiscible Newtonian fluids, right? Two immiscible Newtonian liquids flow steadily between two large parallel plates under the influence of an applied pressure gradient. The lower plate is fixed while the upper plate is pulled, while the upper one is pulled with a constant velocity of 10 meter per second. The thickness H of each layer of the fluid is 0.5 meter. The velocity profile for each layer is given by right? This is the velocity profile. This is the velocity profile. So where A, B, C are constant, right? V1 is 6 plus AY minus 3y square. V2 is B plus CY minus 9y square, where A, B, C are constant. The ratio of the force on the top plate to the force on the bottom plate if mu1 is equal to 10 to the power minus 3 Pascal second, and each plate having surface area of 4 meter square. So beta, this is the diagram for this particular question, right? This is the liquid number 1, this is the liquid number 1, this is the liquid number 2. And for the liquid number 1, that viscosity is mentioned 10 to the power minus 3 Pascal second. Mu1 is equal to 10 to the power minus 3 Pascal second. And please note down, mu2 is also mentioned in the problem. Mu2 is also mentioned in the problem. There is some typing error. So mu2 is not mentioned here, but that is typing error, right? But in this problem, mu2 is given. So mu2 is, let us consider mu2 is 2 into 10 to the power minus 3 Pascal second, right? And this is the coordinate system. This is the coordinate system. So basically in this expression, whatever the expression you see here in this expression, that y is taken from the interface, right? Y is taken from the interface. So beta, this is the interface. This is the liquid interface. So y is taken from the interface, right? And above this reference, above this interface, there is positive y, and below the interface there is a negative y. Above the interface positive y, below the interface negative y. So see, minus 0.520, minus 0.520 when y varies minus 0.520. So minus 0.520, that means, right, in this here this velocity variation, right, here this velocity variation is 6 plus AY minus 3y is, 6 plus AY minus 3y square. 6 plus AY minus 3y square. 6 plus AY minus 3y square. And see, 0 to just 1 minute, na? This is plus, na? This is plus, right? And don't confuse, this is simply V, right? Minus 0.5 to 0, this is the velocity variation, and 0 to plus 0.5, this is the velocity variation. So for this fluid, that velocity variation is u is equal to b plus cy minus 9y square. B plus cy minus 9y square, right? Is it clear to everyone? Till this point, it is clear to everyone now? Okay, so if you see this question, mu2 is not mentioned in the problem, but mu2 is given beta. There is typing error, and that mu2 is 2 into 10 to the power minus 3 Pascal second. And there is some typing error. This is not minus 0.5, this is plus 0.5. So 0 to plus 0.5, right? This gap is 0.5. This gap is 0.5. This gap is 0.5. This gap is also 0.5. Right? This gap is 0.5. This gap is also 0.5. So 0 to plus 0.5, this is the velocity variation, and 0 to minus 0.5, this is the velocity variation. Okay. Now in this question, what is asked? In this question asked the ratio of force on the top plate to force on the bottom plate. So F top plate to, right, shear force, na? Shear force on top plate to shear force in bottom plate, right? Shear force on top plate to shear force on bottom plate. Is it fine? This is the question. What is this ratio? Okay, so beta, can we write this? This is equal to tau shear stress in top plate multiplied by area to shear stress in bottom plate multiplied by area. Can we write in this way now? Can we write in this way now? And area is same for both the plate. For each plate has surface area of 4 meter square. So each plate having same surface area. So this area and area is cancelled out. So ultimately what you are getting, shear stress on top plate to shear stress in bottom plate. Shear stress in top plate to shear stress in a bottom plate. Okay. Now how you calculate the shear stress? How you calculate the shear stress? How you calculate the shear stress? Tell me how you calculate the shear stress. Tell me how you calculate the shear stress by the Newton's law of viscosity. Right? Both the fluids are the Newtonian fluids, so we can apply the Newton's law of viscosity. Right? So we can write shear stress experienced by the top plate. This is mu1 into du by dy at the top plate divided by. Now what is the tau bottom? What is the tau bottom? What is the shear stress experienced by this fluid? So we can write this is the mu2, because plate number 2 is in contact with the liquid number 2. So mu2 into this is du by dy in bottom plate. Right? Or better simply we can write mu1 multiplied by du by dy at y is equal to plus 0.5 upon mu2 into du by dy at y is equal to minus 0.5. Right? We can write in this way. Is it clear? Now this is equal to what is the mu1? That mu1 is 10 to the power minus 3. What is the mu1? That mu1 is 10 to the power minus 3. Now calculate du by dy. Calculate du by dy for this velocity profile. So du by dy is equal to, this is c minus 18y. Correct na? C minus 18y. Now du by dy at y is equal to 0.5 meter. Du by dy at y is equal to 0.5 meter. So put the value of y as 0.5. Put the value of y as 0.5. So c minus, right? C minus, this is 18 multiplied by 0.5. 18 multiplied by 0.5. So it comes 9. So this is c minus 9. Is it fine? Now calculate du by dy for this velocity profile. So du by dy is equal to, this is a minus, right? This is 6y. Now calculate du by dy at y is equal to minus 0.5, minus 0.5. So this is equal to a minus 6 multiplied by 0.5. So this equal to a plus, right? A plus 3. Right, so simply we can write du by dy at y is equal to plus 0.5. At y is equal to plus 0.5. This is c minus 9 upon du by dy at y is equal to minus 0.5. That is a plus 3. Right. So this is the ratio. This is the ratio of shear force experienced by top plate to bottom plate. This is the ratio of shear force experienced by top plate to bottom plate. Now beta tell me, can we find out this constant C and A? Can we find out the C and A? Tell me, can we find out the C and A? Can we find out the C and A? Tell me, can we find out the C and A? Tell me fast. Yes, by using the boundary conditions. Okay, before that, beta, can anyone tell me what is the value of B? Can anyone tell me what is the value of B? Right, before calculating the value of A and C, can anyone tell me what is the value of B? What is the value of B? So beta, that is very simple, na? That is very simple. See, at y is equal to 0. At y is equal to 0. See, at y is equal to 0. At y is equal to 0. Right, that means at the interface. At the interface. At the interface. At the interface. and at the interface means y is equal to 0. So can we write now? Can we write now V1 is equal to V2? Can we write now V1 is equal to V2 at the interface? Beta, at the interface, that fluid layer velocity is same now. So we can write V1 is equal to V2. V1 is equal to V2, right? At y is equal to 0. At y is equal to 0. So that V1, B plus Cy minus 9y square, right? B plus Cy minus 9y square is equal to 6 plus ay minus 6 plus ay minus 6 plus ay minus 6 plus ay minus 3y square. 3y square. Now at y is equal to 0. So at y is equal to 0, this term is finished. This term is finished. This term is finished. This term is finished. Y is equal to 0. So ultimately what you are getting? Ultimately that b is equal to 6. B is equal to 6. Right? B is equal to 6. Is it clear? And also at the interface we know that also at the interface also we know that at the interface that tau1 is equal to tau2 now, right? Also at the interface that tau1 is equal to tau2. Remember this concept, beta? Remember this concept or not? Remember these concept or not? I already explained the application of Newton's law of viscosity. I discussed around 10 to 11 cases. So I hope you remember these concepts, right? At the interface, tau1 is equal to tau2. So simply we can write tau1 is equal to mu1 du by dy at y is equal to 0, right? Because at the interface y is 0. This is equal to mu2 into du by dy at y is equal to 0, right? Okay, so this is 10 to the power minus 3. That mu1 is 10 to the power minus 3. Now what is the du by dy? What is the du by dy? That is c minus, that is c minus, right? C minus 18y, c minus 18y. That is equal to mu2, 2 into 10 to the power minus 3 into, now du by dy. So du by dy is a minus 6y, a minus 6y, a minus 6y. And y is equal to 0. At y is equal to 0, this term is finished, this term is finished. So ultimately what you are getting, right? 10 to the power minus 3, 10 to the power minus 3 is also cancel out. So this is c is equal to 2a, or we can say, right? Okay, fine. C is equal to 2a. C is equal to 2a. Right? C is equal to 2a. Fine. So you are getting C is equal to 2a. C is equal to 2a. But we need separate value of C and A. Right? We need separate value of C and A. Okay, so do one thing. We have another boundary condition. Beta, can we write at y is equal to, can we write, see here, can we write at y is equal to plus 0.5, the u is equal to 10 meter per second, at y is equal to plus 0.5 meter, that u is equal to 10 meter per second now, right? At y is equal to 0.5 meter, u is equal to plus u is equal to 10 meter per second now. Fine. Now the plate number 1 is in contact with the liquid number 1, and liquid number 1, this is the velocity profile. So we can write u is equal to b plus cy minus 9y square, right? So at y is equal to plus 0.5, u is equal to 10. So this is 10. This is b plus c multiplied by 0.5 minus 9 multiplied by 0.5 square, right? We already calculate the value of b, right? We already calculated the value of b. So value of b is, right, that value of b is 6, right? So this is 10 is equal to, this is 6 plus c into 0.5 minus 9 into 0.5 square. So beta, tell me what is the value of C. So tell me what is the value of C. What is the value of C? Which last step beta? This one at the interface. You are talking about this. You are talking about this step, or which step? Now calculate C. Calculate C. So this is 10 plus 9 into 0.5 square, right? 10 plus 9 into 0.5 square minus 6 by 0.5. So this comes C is equal to 12.5. Everyone getting this? C is equal to 12.5. C is equal to 12.5. And once you know the value of C, so we can find A is equal to 12.5 by 2. Right, so this comes 6.25. 6.25. This is the value of A. Right, now see here. This is equal to this is C minus 9. Na? Just 1 minute beta. This is mu1 mu2 du by dy y is equal to 0.5. So this is C minus 9. Na? I'm sorry beta. This is C minus 9 upon, right? This is A minus, sorry, this is A plus 3. Sorry, this is A plus 3, right? And 2. Because mu2 is 2 into 10 to the power minus 3 and mu1 is 10 to the power minus 3. Now put the value. So value of C is 12.5 minus 9 divided by, right, that value of A is 6.25 plus 3 into 2. Right, so tell me what is the ratio that you are getting. So tell me what is the value of shear force on a top plate to shear force on a bottom plate. So tell me this value. So 12.5 minus 9, 6.25 plus 3. Right, 12.5 minus 9 upon 6.25 plus 3 into 2. So I think this comes 0.189. This comes 0.189. This comes 0.189. This comes 0.189. So this is the answer. Right? This is the answer. Fs top plate to Fs bottom plate, this ratio becomes 0.189. This is the answer. So tell me, everyone getting the same answer? Tell me, everyone getting the same answer? Okay, so is it clear? This question is clear or not? This question is clear or not? Tell me. Fine. Okay, now come to the next concept beta, or next fluid property. Come to the next fluid property, right? Fluid property number 7, I think. 7 or 8? Come to the next fluid property. Property number 7 or property number 8? After kinematic viscosity, this is the next property. After kinematic viscosity, this is the next property, right? So property number 7, compressibility or bulk modulus. So actually, what is the compressibility, right? What is the compressibility? So beta, actually compressibility shows how easily we can compress the fluid under 3-dimensional compression. We know that fluid resists, right? Fluid resists 3-dimensional compression only, right? We already discussed in the basic classes. Remember, I think class number 2 or class number 3, I already discussed this part, right? Fluid only resists 3-dimensional compression. Fluid never resists 1-dimensional compression. Fluid never resists two-dimensional compression. Fluid only resists the three-dimensional compression. So compressibility is defined in terms of the three-dimensional compression, right? What is the compressibility? What actually it shows? That compressibility shows how easily we can compress a fluid under three-dimensional load or under three-dimensional compression. And how you can measure the compressibility, right? How you can measure the compressibility of any fluid? So coefficient of compressibility, that is denoted by beta. So coefficient of compressibility is actually measure of compressibility, right? Coefficient of compressibility is actually measure of compressibility. And if compressibility, right, if compressibility of fluid is more, what is the meaning of that? If compressibility of fluid is more, what is the meaning of that? If compressibility is more, that means that fluid is easy to compress, right? When I say compressibility of fluid is more, that means that fluid is easy to compress, right? So the coefficient of compressibility is the measure of coefficient of compressibility, coefficient of compressibility, coefficient of compressibility, that is denoted by beta, is the measure of compressibility, right? So what is the coefficient of compressibility? How you define the coefficient of compressibility? So beta, coefficient of compressibility is nothing but it is relative change, it is relative change in volume, relative change in volume of fluid, relative change in volume of fluid with respect to change in pressure, with respect to change in pressure, with respect to change in pressure, right? What is the compressibility? What is the coefficient of compressibility? So coefficient of compressibility is nothing but it shows the relative change in volume of fluid with respect to change in the pressure. Fine. So, right, coefficient of compressibility, it shows relative change in volume with respect to change in pressure. So for understanding this, let us consider a piston cylinder arrangement, right? Let us consider a piston cylinder arrangement like this, right? So let us consider this is a cylinder, and in this cylinder there is a piston. In this cylinder there is a piston. This is the piston, right? This is the piston, right? And this cylinder contains a fluid, right? This cylinder contains a fluid. So this is the fluid, right? This is the fluid. This is the fluid. Right? Now let us consider a small fluid element here. Let us consider a small fluid element here. Let us consider a small fluid element here. So this is the small fluid element. So if you exaggerate this small fluid element, or if you draw the free body diagram of this small fluid element, if you draw the free body diagram of this small fluid element, so see here beta, this is the free body diagram of this small fluid element. This is the free body diagram of this small fluid element, right? This is subjected to pressure P, pressure P, pressure P, right? This is subjected to pressure P, right, like this. So this is the free body diagram of this small element. Fine. Okay, now let us consider when pressure is P, right? When the pressure is P, then volume is, when the pressure is P, then the volume of the fluid is V. Let us consider when the pressure is P, then the volume of the fluid, let us consider that is V. Now, if I increase the pressure by dP amount, if I increase the pressure by dP amount, so let us consider that is P plus dP. So beta, what about the volume? When you increase the pressure, then what happened with the volume? Definitely that volume decreases. So when pressure is raised to P plus dP, then volume is lowered by V minus dV, or volume is lowered to V minus dV. Right? Yes, absolutely correct. When pressure increases, then definitely volume decreases. Okay. Now see, if I am talking about the change in volume, right? If I am talking about the change in volume, so beta, what is the change in volume? If I am talking about the change in volume, so what is the change in volume? The change in volume is dV. And if I ask you what is the relative change in volume with respect to the initial condition or with respect to the initial state, so we can say relative change in volume. So what is the relative change in volume? So simply we can say this is dV by V. Is it fine? So what is the actually compressibility? What is the coefficient of compressibility? So coefficient of compressibility beta is equal to, this is the relative change in volume with respect to relative change in, or sorry, with relative change in volume with respect to change in pressure, And we also know that when pressure increases, volume decreases. We also know that when pressure increases, volume decreases. So put minus sign here to make coefficient of compressibility as positive. Right? Put minus sign here to make coefficient of compressibility as positive, because we know that as pressure increases, volume decreases. Or you can say the negative sign shows, right? Or you can say negative sign shows as pressure increases, volume decreases. As pressure increases, volume decreases. Is it fine? Okay. Now beta, this change in volume to original volume, this is also we can say volumetric strain, right? Change in volume to original volume, this also we can say volumetric strain. Na? This is nothing but the volumetric strain. Na? This is nothing but the volumetric strain. Na? This is the volumetric strain. Tell me yes or no. Tell me yes or no. This is the volumetric strain. This is the volumetric strain denoted by epsilon V. This is the volumetric strain. Tell me yes or no. Denoted by epsilon V. So we can write coefficient of compressibility as beta is equal to relative change in volume with respect to relative change in volume, or we can write in this way, minus dV by V dP. Right? Or we can say volumetric strain. Right? The dV by V is nothing but the volumetric strain. So beta, if you see here, for given pressure change, if you see here, for given pressure change, for given pressure change or for given dP, if beta is more, for given pressure change, if beta, that means coefficient of compressibility is more, then volumetric strain is more. And volumetric strain is more, that means change in volume is more. And change in volume is more, that means that fluid is easy to compress. So whenever I say higher value of the beta, so higher value of beta means, right, higher value of beta means easy to compress, as simple as. Higher value of beta means more volumetric strain, right? Higher value of beta means easy to compress, as simple as. Is it fine? Is it okay? Fine. Now beta, this is the one mathematical expression of the coefficient of compressibility. Can we write this mathematical expression in terms of density or in terms of density? Can we write this mathematical expression in terms of density? Can we write this mathematical expression in terms of density? Yes, sir, we can write. Now tell me, when you increase the pressure, then there is any change in the mass of the fluid, right? When you increase the pressure from P plus dP, right? Sorry, when you increase the pressure from P to P plus dP, so any change in the mass of the fluid? Any change in the mass of the fluid? Tell me. No, mass of the fluid does not change. Mass of the fluid does not change. So we can say, we know that mass is constant, right? Mass of the fluid is constant. And you remember mass density, beta? You remember mass density, na? The mass density is nothing but the mass per unit volume. So we can write mass is equal to rho multiplied by volume is equal to constant. Okay, now take derivative both sides. So if you take derivative both sides, so derivative of constant is 0. So we can write rho dV plus V d rho is equal to 0, right? Or we can write rho dV minus V d rho, or we can write minus dV by V is equal to, this is d rho by rho, right? So in this expression, instead of minus dV by V, can we write d rho by rho now, right? So beta is also defined as dV by V dP. This is also defined as, this is d rho by rho dP, right? So this is the mathematical expression of beta. In terms of the volumetric strain and in terms of the relative change in density. So this is the mathematical expression of beta, right? Is it clear to everyone? Is it clear? Okay, now come to the next property. See, coefficient of compressibility shows how easy to compress, right? If I'm talking about the coefficient of compressibility, so coefficient of compressibility shows how easy to compress a fluid, right? There is another fluid property which is a reverse of this coefficient of compressibility. The coefficient of compressibility shows how easy to compress a fluid. There is another property which shows how difficult to compress a fluid, and that fluid property is known as the bulk modulus, right? That fluid property is known as the bulk modulus. So the bulk modulus is nothing but that, beta. The bulk modulus is nothing but the reciprocal of the compressibility, right? Bulk modulus is nothing but the reciprocal of compressibility, and bulk modulus shows how difficult for the fluid to compress. So it is very simple that bulk modulus is and bulk modulus is denoted by K, right? Bulk modulus is denoted by K. Right? And this bulk modulus is equal to 1 upon compressibility. 1 upon compressibility. Right? So simply K is equal to 1 by beta. Or we can write dP by dV by V, or we can write d rho by, right, or we can write dP by d rho by rho. Right? So for a given pressure change, for a given pressure change, for a given pressure change, that means for a given dp, if K is more, that means volumetric strain is less. For given pressure change, if K is more, then volumetric strain is less, right? That means if K value is high, then it is difficult to compress a fluid. If K value is high, then it is difficult to compress the fluid. Is it fine? Okay. Now if you compare beta and K of solid, liquid and gas, if you compare solid, liquid and gas, if you compare beta and K value of solid, liquid and gas, so what is the order? If I'm talking about the beta, if I'm talking about the compressibility, so which out of this, which one is easy to compress? Solid, liquid and the gas. So out of the three, which is easy to compress? So obviously gas is easy to compress, na? Gas is easy to compress. So if I'm talking about the beta, so beta of gas is highest, then beta of liquid, and least beta is for the solid. Right? So compressibility is highest for the gas and least for the solid. And if I'm talking about the bulk modulus, so just opposite, right? K of solid, then K of liquid, and least K of gases, right? And what is the value? What is the unit of K? Beta, what is the unit of K? So this is the unitless, na? That's dV by V is the unitless. The dV by V is the volumetric strain, that is the unitless. So what is the unit of K? The unit of K is Newton per meter square, right? Unit of K is Newton per meter square, or you can say Pascal, right? Whereas a beta is the reciprocal of K. So what is the unit of beta? That is meter square per Newton, right? So we remember this, right? Pressure unit and K unit, pressure unit and the bulk modulus unit are same, right? So what is the unit of bulk modulus? The bulk modulus unit is Pascal, or you can say Newton per meter square. Okay, now if I'm talking about the liquids, right? Now come to the fluid part. If I'm talking about the liquids, for liquids. So theoretically, can anyone tell me what is the beta? Theoretically, right? What is the beta for liquids? What is the beta for liquids theoretically? Can anyone tell me what is the beta? What is the beta for liquids? So beta, it is very simple, na? Liquids are incompressible, right? Liquids are incompressible, na? We know that this part, na? If I'm talking about the liquids, so theoretically liquid is difficult to compress, right? Liquid is difficult to compress. So if I'm talking about the compressibility of liquids, so theoretically that compressibility of liquid is 0, theoretically, right? And if beta is 0, then what about the bulk modulus? The bulk modulus is infinite. This is the theoretically, right? So in a theoretical way, we can say the compressibility for the liquid is 0, whereas the bulk modulus is infinite, because we know that liquid are incompressible. We know that, na? Liquids are incompressible. We know that liquids are incompressible. Remember, na? Remember, right? Example of water. So liquids are incompressible. Generally, we treated liquid as incompressible. So liquid are incompressible, and we know that if liquids are incompressible, then what is the change in volume? That change in volume is zero, right? What is the change in volume? The change in volume is zero. What is the change in density? The change in density is zero. So we can say volume is constant. We can say volume is constant. We can say density is constant for incompressible substance, right? Or we can say beta compressibility is zero, or we can say bulk modulus is infinite. So if anyone asks you, right, if there is a fluid which is a incompressible, so what is the meaning of the incompressible? So you can say for incompressible substance or incompressible liquid, the change in volume is zero or volume is constant, change in density is zero or density is constant, right? Compressibility is zero, or you can say bulk modulus is infinite, right? Now this is for liquid. Now come to the gases, right? Come to the gases for gases. So beta, actually what happened in case of the gases? In case of the gases, we are not talking about a single compressibility. We are talking about the different compressibility. Why? Because in case of the gases, compressibility or bulk modulus depends on the type of the process, right? If I'm talking about the gases, please try to understand these things. If I'm talking about the gases, so beta, in case of the gases, there is not single compressibility, right? That compressibility or bulk modulus depends on the type of the process, which kind of the process occurs. So let us consider, right, for gases, and that gases are considered as ideal gases, right? So if in a gas process is a isothermal, if in a gas process is isothermal, everyone knows the isothermal now. What is the meaning of isothermal? If I ask you what is the isothermal process, what is the isothermal process? What is the isothermal process? Isothermal process, that means temperature is constant, right? So when the process is isothermal, right, when the process is isothermal, then isothermal compressibility come into picture. Then isothermal compressibility come into picture, and isothermal compressibility is denoted by beta T. And in a similar fashion, isothermal bulk modulus come into picture, and isothermal bulk modulus is noted by Kt if process is a isothermal in a gas. Similarly, in a gas, if process is reversible adiabatic, and everyone knows if reversible adiabatic means isentropic, right? Reversible adiabatic means isentropic, entropy constant, right? Reversible adiabatic means isentropic. So if reversible adiabatic process occurs in an ideal gas, then we can use this law, PV to the power gamma is equal to constant, right? If reversible adiabatic process occurs in an ideal gas, then we can write PV to the power gamma is equal to constant. Or if I ask you, in case of the reversible adiabatics that occurs in an ideal gas, so what is the relation between P and V? So you can say, sir, in case of the reversible adiabatic process that occurs in an ideal gas, so we can write PV to the power gamma is equal to constant. Fine. So in case of the reversible adiabatic process or isentropic process, there is a adiabatic compressibility. There is a adiabatic compressibility. Adiabatic compressibility. And if I'm talking about the bulk modulus, there is a adiabatic bulk modulus. Adiabatic bulk modulus. Is it clear? Tell me, is it clear or not? Is it clear or not? Tell me. Is it clear or not? Right. So adiabatic compressibility. So we can write K. Sorry, adiabatic compressibility. So we can write beta adiabatic and adiabatic bulk modulus. So we can write K adiabatic. Right. We are talking about the gases now, beta. We are talking about the gases because in case of the gases, compressibility and the bulk modulus depends on the type of the process. So if process is a isothermal, then isothermal compressibility and isothermal bulk modulus come into picture. And if the process is reversible adiabatic, or simply we can say adiabatic or isentropic, then adiabatic compressibility and adiabatic bulk modulus come into picture. So let's discuss about the isothermal compressibility and isothermal bulk modulus. Let's discuss about the isothermal compressibility. Let's discuss about the isothermal compressibility. Isothermal compressibility. Let's discuss about the isothermal compressibility and isothermal bulk modulus. Isothermal compressibility beta T and isothermal bulk modulus. Isothermal bulk modulus, that is K. Right. Now see, we are talking about the ideal gas now. So we know the ideal gas equation, right? We know the ideal gas equation. So from ideal gas equation, we know the ideal gas equation, correct na? Everyone knows the ideal gas equation now, that PV is equal to, right, PV is equal to RT or PV is equal to MRT. Just 1 minute. PV is equal to, this is PV is equal to MRT. This is the ideal gas equation. PV is equal to MRT. Everyone knows this. PV is equal to MRT. Right? Or we can write P is equal to, that is rho RT. Or we can write P is equal to rho RT. Fine. Now see, if I'm talking about the isothermal, compressibility, right? Now do one thing. Isothermal means temperature is constant. So we can write rho is equal to P by RT. Right? Rho is equal to P by RT. Right? Now see here. Right? Now see here. Differentiate this with respect to P. So d rho by dP is equal to, this is 1 upon RT, because isothermal, so temperature is also constant. So differentiate rho with respect to pressure. So we can write d rho by dP is equal to 1 upon RT. And also better that 1 upon RT, we from here 1 upon RT is equal to rho by P. 1 upon RT is equal to rho by P. So we can write 1 upon RT is equal to rho by P. Right? So d rho by dP is equal to rho by P or simply we can write this is d rho by rho upon dp, right? This is equal to 1 upon p. This is equal to 1 upon p. So tell me what is this? Beta, tell me what is this, right? What is this? D rho by rho. See the d rho by rho. See here, that d rho by dp. This is nothing but the beta only, na? That is nothing but the beta only, na? This is nothing but the beta only. This is nothing but the beta only. So beta in terms of beta in case of the isothermal case, right? So this is the isothermal compressibility, and this is nothing but the 1 upon p. This is nothing but the 1 upon p. So this is the isothermal compressibility. This is the isothermal compressibility. And we know that, right? We know that isothermal compressibility beta T is equal to 1 by P. So tell me about isothermal bulk modulus. What is the isothermal bulk modulus? Isothermal bulk modulus. So tell me what is the isothermal bulk modulus? So we know that bulk modulus is the reciprocal of the compressibility. So K isothermal, right? K isothermal is equal to 1 by beta T, and this is nothing but the P, right? So in case of the isothermal process, in case of the constant temperature process for a gas, this is compressibility and the bulk modulus. Fine. Is it clear? Tell me, is it clear? So can we calculate in terms of the adiabatic condition? Can we calculate in terms of adiabatic condition? Can you calculate in terms of adiabatic condition? Adiabatic condition. Adiabatic compressibility. Adiabatic compressibility and adiabatic compressibility and adiabatic bulk modulus. Okay, so find out how you can start. How you can start. So start from the relation between P and V. Right? So P V to the power gamma, we know that reversible adiabatic and ideal gas combination, right? Reversible adiabatic and ideal gas combination, we can write PV to the power gamma is equal to constant. PV to the power gamma is equal to constant. So let's see. PV to the power gamma is equal to constant. Beta, and also we know that specific volume is the reciprocal of density. We know this, right? Specific volume is the reciprocal of density. So we can write this is P rho to the power gamma is equal to constant, or we can write P is equal to C into rho to the power gamma. Fine. Now find out the dP by d rho, right? Differentiate with respect to density. So dP by d rho is equal to, this is C multiplied by, right, gamma into rho to the power gamma minus 1. What is the gamma? Can anyone tell me, beta, what is the gamma? That gamma is What is the gamma? The gamma is adiabatic index, right? What is the gamma? The gamma is a adiabatic index, and this is ratio of gamma is a adiabatic index, and this is ratio of specific heat at constant pressure to specific heat at constant volume, right? Gamma is the ratio of specific heat at constant pressure to specific heat at constant volume, and the value of gamma depends on type of the process or type of the gas. The value of gamma depends on the type of the process or type of the gas. Whether the value of gamma depends on value of gamma depends on type of gas, right? Value of gamma depends on the type of the gas, right? So type of the gas means, beta, your ideal gas may be monoatomic. Your ideal gas may be monoatomic, right? Monoatomic, single atom, like helium, neon, xenon, right? Like that. So monoatomic, right? Like helium, argon, right? Xenon, like this. So your ideal gas may be monoatomic. Your ideal gas may be diatomic. Your ideal gas may be diatomic, right? Diatomic means like H2, O2, N2, like that. Air also diatomic, right? Or your ideal gas may be polyatomic. Your ideal gas may be polyatomic. Polyatomic means like CH4, CO2, right? Ammonia, like that, right? That is under polyatomic. So in case of monoatomic, what is the value of gamma? In case of monoatomic, what is the value of gamma? That is 1.67. For the monoatomic gas, what is the value of gamma? That is 1.67. For diatomic gas, what is the value of gamma? The value of gamma is 1.4, right? And for the polyatomic gases, what is the value of gamma? Gamma is 1.33, right? For polyatomic gases, what is the value of gamma? That value of gamma is 1.33. So the value of gamma, which is the adiabatic index, that depends on the type of the gas, right? So remember this part, right? Remember this part. Fine. Now come to here. So dp by d rho, right? If you differentiate this term, then what you are getting, dp by d rho is equal to C gamma rho to the power, right? C gamma rho to the power gamma minus 1. Now do one thing, multiply it by density both side. If you multiply it by density both side, then what you are getting, rho dp by d rho is equal to, this is C multiplied by, right? C multiplied by gamma into rho to the power gamma. Fine. And C into rho to the power gamma. C into rho to the power gamma is nothing but the P. So this is the gamma into P. And this is the rho dP by d rho, right? Or we can write d rho by rho dP is equal to 1 upon gamma P, right? D rho by dP is equal to 1 upon gamma P, and this is nothing but the beta. This is nothing but the beta. And since we are talking about the adiabatic condition, so beta for adiabatic condition is 1 upon gamma P. This is the beta, right? This is the adiabatic compressibility. And if you know the adiabatic compressibility, if you know the adiabatic compressibility, which is 1 upon gamma P, so we can easily say about adiabatic bulk modulus. And adiabatic bulk modulus is reciprocal of this, and this is the gamma p. Right? So this is about the adiabatic compressibility and the adiabatic bulk modulus. Is it okay? Is it okay or not? So if I'm talking about the gases, see, if I'm talking about the gases, so in gases, if I'm talking about the gases, so which gas? Ideal gas, obviously. Right? Which gas? Ideal gas. So if I'm talking about the ideal gas, so one process is a constant temperature process, and another process is reversible adiabatic process. Another process is reversible adiabatic, or you can say isentropic. Isentropic, and that is isothermal. So if your process is isothermal, then what is beta T? That beta T is 1 upon P. And what is the bulk modulus? So that is P. Right? Now, if I'm talking about the reversible adiabatic process, so what is the beta? That is gamma P. And what is the K adiabatic? Right, this is 1 upon gamma P, na beta? This is 1 upon gamma P. 1 upon gamma P. So this is equal to gamma P. This is equal to gamma P. Is it fine? Is it okay? Tell me, is it okay or not? Right, and also we can find the relation. Adiabatic compressibility is gamma times of isothermal compressibility. And similarly, adiabatic bulk modulus is gamma times of isothermal bulk modulus. Right? So remember this relation. Right? Remember this relation. Okay, so this is about the isothermal compressibility, isothermal bulk modulus, adiabatic compressibility, and the adiabatic bulk modulus. Okay, so I hope whatever we discussed in today's class, that is clear to everyone. I hope. Any doubt? Any doubt? Till this point, any doubt? Till this point, any doubt? No? Adiabatic, na? Adiabatic. Okay. Now come to the next property. Next property is velocity of propagation of sound in a medium. Right? Velocity of propagation of sound in a medium, or velocity of pressure wave in a medium. Velocity of propagation of sound in a medium, or velocity of pressure wave in a medium. So whatever the velocity of sound in a medium, the same is applicable for the pressure wave also. Right? So you can say acoustic velocity, na? You can also say acoustic velocity in medium. So beta, if I'm talking about the acoustic velocity, or sound velocity in a medium, that is denoted by C. It depends on the medium bulk, it depends on the bulk modulus of a medium and density of a medium. Right? So C is equal to, this is root over K by rho. That C is equal to root over K by rho. And what is the K? What is the K? K is the bulk modulus of medium. K is the bulk modulus of medium. K is the bulk modulus of medium. And what is the rho? The rho is density of medium. Right? So this is the mathematical expression of the acoustic velocity in a medium. Fine. Now see, if I'm talking about the adiabatic condition, right? If I'm talking about the adiabatic condition, adiabatic plus, right? Adiabatic plus ideal gas condition. Adiabatic means reversible adiabatic, na? Reversible adiabatic, or you can say isentropic, So reversible adiabatic condition per plus ideal gas. So beta we can write that K is equal to gamma times of P now. We can write K is equal to gamma times of P now. We already discussed this. See, K is equal to gamma times of P. K is equal to gamma times of P. Right? So that in particular case we can write that acoustic velocity is equal to root over gamma P by rho. Gamma P by rho. And we know the ideal gas equation. That ideal gas equation is PV is equal to MRT, or we can write P is equal to rho RT. And if you find out the P by rho, so P by rho is equal to RT. Right? P by rho is equal to RT. So what we can write? We can write that C is equal to root over that P by rho is equal to RT. So this is the gamma RT. Right? So this is a very, very important expression. That acoustic velocity in a medium under adiabatic condition, under isentropic condition, and substance or medium is an ideal gas, then in that particular case we can write C is equal to root over gamma RT, where gamma is the adiabatic index, na? We already discussed this. Gamma is a adiabatic index, right? Gamma is a adiabatic index. What is the R? That R is a characteristic gas constant. Right? R is a characteristic gas constant. And what is the T beta? T is the absolute temperature. And absolute temperature means in Kelvin, right? So gamma is the adiabatic index, and remember this R in this expression, put R in joule per kg Kelvin, right? In this expression, that characteristic gas constant, put characteristic gas constant in joule per kg Kelvin. So if you put R in joule per kg Kelvin and T is in Kelvin, then this C is in meter per second. C is the acoustic velocity or velocity of sound in a medium, right? That is in meter per second, right? And you also must know the relation between characteristic gas constant and the universal gas constant, right? Characteristic gas constant and the universal gas constant. You must know this relation between R and R bar, right? Relation between R and R bar. So what is the R bar? That R bar is a universal gas constant. R bar is a universal gas constant, and that R bar is 8.314 kilojoule per kilomole Kelvin, right? So what is the relation between R and R bar? So R is equal to R bar upon molecular weight of the gas. Right? So this is the relation between R and the R bar. So you must know this relation. You must know this relation. For mechanical and chemical student, you already know this relation, right? For mechanical and chemical student, you know this relation. For civil student, maybe this relation is new, but you must know this relation also, right? R is equal to R bar upon molecular weight of the gas, where R bar is a universal gas constant. And why it is called why R bar is called universal gas constant? Because that R bar is same for every gas, right? The R bar does not change gas to gas. If you consider oxygen, that R bar is 8.314. If you consider nitrogen, R bar is 8.314. If you consider CH4, that R bar is 8.314, right? This R is a characteristic gas constant. That R is a characteristic gas constant, and it varies gases to gases. So if you consider oxygen, R is different, right? If you consider nitrogen, R is different. If you consider CH4, R is different. So this is the characteristic gas constant, and this is the universal gas constant. So I hope you can understand this, right? Fine. So beta, whatever we discussed in today's class, I hope that is clear to everyone. So remaining part we will discuss in tomorrow's session, right? So in tomorrow's session we will discuss about the surface tension concept, a very beautiful concept and also very important concept, surface tension concept. And after that we discuss about the capillarity and all. Okay, so I hope whatever we discussed in the class, that is clear to everyone. So any doubt? No doubt? Fine. Okay, so thank you so much guys, and bye bye, take care, and good night everyone.